Welcome, folks, to this episode of Lessons from the Cockpit. I am your host, Mark Hasera, here for our 9th episode. Special thanks to the book, Tanker Pilot, Lessons from the Cockpit, for sponsoring this episode, which you can find at Amazon.com in all 4 formats: hardback, softback, Kindle, and Audible. Our show debriefs some of the most amazing pilots, aircrew members, maintainers, and aviation enthusiasts from all over the world. On our show, we investigate tactics, techniques, and procedures, but more importantly, lessons learned. What did you learn from the experience of these pilots and aircrew members that went through these extreme and extraordinary military, commercial, or private flight operations? This exploration is designed to give you, our listeners, practical advice on how does the aviation world work and expand critical thinking skills in the air and on the ground. On today's show, we're going to answer the question, what does a bird of prey, a woman's orifice, and President Nixon all have in common when you're talking aviation? Today, we're going to talk about the power to fly. So, grab an adult beverage of your choice, sit down, strap in, and let's begin the Lessons from the Cockpit show. As airplane designers sit down with a blank sheet of paper to create a new airplane, there are 3 factors that go into every airplane. Sometimes they use all 3, sometimes they use 1, sometimes just 2. But these 3 factors are the most important thing to think about when designing a new airplane. Those 3 factors are range, how far can I go? Payload, how much can I carry? Endurance, how long can I stay up? When designing an airplane with range, payload, and endurance, it always comes down to a couple of very important things that are in the design. One of those most important things is the engine, the power to fly, the power to keep the airplane in the air, to give it range, payload, or endurance. When you're fighting in combat in a fighter plane, speed and range are very important. When you're flying tankers, it's range and endurance. How far can I go? How much gas can I offload? How far can I come back? These are the factors that make up airplane design. And in Air Force doctrine, they always speak of range, payload, and endurance in all of the air mobility doctrine manuals. In the late 1930s, the Royal Air Force in Britain needed new fighters, and they needed them desperately, because in 1938, Time Magazine's Man of the Year was rising in Europe and was invading. Adolf Hitler had invaded Czechoslovakia, then Poland, then Denmark, the Netherlands, and France. He had said in several of his speeches, Germany's main enemy is the British. And now the Luftwaffe has bases only 150 miles from London, the United Kingdom's capital, with all of the airfields scattered around it. Hitler knew if he was to take over Europe under his dictatorship, he had to defeat the British. His military generals got together and created Operation Sea Lion, the invasion of England from France. They moved all of these supplies to do it. There was boats and soldiers and all kinds of material, particularly near Calais, which is the shortest distance between the British mainland and France. But there was one thing stopping them, and that was air superiority over the British homeland. The Luftwaffe would have to fight for air supremacy over the British mainland, knocking out the Royal Air Force in order for them to safely invade the British homeland. The British had 2 brand new airplanes that were just showing up at this critical time in their Royal Air Force fleet. The Hawker Hurricane and the Supermarine Spitfire. A great aero engineer by the name of R.J. Mitchell created this fantastic fighter airplane, and it was built around an engine made by Rolls-Royce. And when Rolls-Royce named engines, they always named them after some type of bird of prey. And Rolls-Royce named this particular engine after Merlin, the bird of prey, a hawk-like bird that dives down on its prey at fast speeds. The Merlin engine becomes famous world over, and some of them are still flying today that were manufactured back in the 1940s. The Supermarine Spitfire, Mark I, Mark IIs, were very maneuverable, had 303 caliber machine guns, and were basically defending the homeland of Great Britain. In the initial dogfights, though, with the Messerschmitt Me-109s, the early versions of it, they found one problem with the engine. And it was a serious problem. Pilots were dying because of this problem. The Merlin engine used standard carburation. The Me-109 had fuel injection. And in those carburetors, when they would go into negative G maneuvers, the fuel was still pumping in, but wasn't going through the carburetor system. So it was collecting in the carburetor and flooding the engines in negative G maneuvers. And it would flood the engine so that it sputtered or even cut out for as much as 1 to 3 seconds in combat. And 1 to 3 seconds is a very long time in air combat. The Germans knew this was a problem. And so whenever they wanted to escape from the Hawker Hurricane or the Spitfire, they just go into a negative G bunt. Just push the nose over. The Spitfire pilots and the Hurricane pilots realized that they needed to go into about 90 degrees of bank and let the nose fall to keep kind of 1G on the airplane to keep the fuel going. But they had to have a solution to this problem, because you can't have the engine cutting out in combat when you're behind a guy, you're about to shoot him down, or worse yet, somebody's behind you about to shoot you down. The RAF went out and said to the Royal Air Establishment, we've got a problem and we've got to fix it. Rolls-Royce, how are you going to do this? And a brilliant engineer working at the Royal Air Establishment comes up with a simple solution. At the age of 14, this engineer was given a motorbike and began racing. Loved racing. In order to make the motorbike go faster, what do? You work on the engine. You make the engine more effective, more horsepower. And the key to that is in the carburation. And this aero engineer had been working on motorbike carburation and was an expert at how to aspirate engines. This aero engineer gets the problem and starts tinkering with it all and figures out, we can put a little brass-like thimble to restrict the flow of fuel into the engine so it doesn't flood. By putting a hole in the top of it, it will still allow fuel to go into the carburation system. The engine won't sputter. Later on, this same engineer figures out, we don't actually need that little cup thimble thing. Maybe all we need is this little washer type thing. They make one, they go out and they test it, and it works fabulously. A team of engineers from the Royal Air Establishment now go out to all the bases and start modifying all the carburetors in all the Merlin engines. Here's the surprise about this. This aero engineer was one of the first people of her gender to go through Manchester University and get her aero engineering degree. We've seen the movie Hidden Figures, Katherine Johnson and the other 2 gals that work at NASA. But Beatrice Schilling, her friends called her Tilly, is the engineer that comes up with that little thimble and later washer plate to go in the carburetor. Now, of course, all pilots flying for the RAF, flying Merlin engine airplanes, are ecstatic about this thing. This thing is fabulous. Now the engine doesn't cut out. And of course, they've got to give it a name. And the name that they give this little thimble is Tilly's Orifice. And Tilly's Orifice saves countless lives because now the engine operates like it's supposed to in combat. It's a fabulous story, folks. Go and look up Beatrice Schilling and read about her because she's got a very colorful lifestyle. She's not... She doesn't take too kindly to male authoritarianism, and she actually pushes back to a lot of her leadership. But she races through her entire life until well into her late age. She races not only motorbikes at 100 miles per hour. She has a gold star for going faster than 100 miles per hour on a motorbike, but she also races cars. But Tilly's Orifice saves countless lives during the Battle of Britain. The RAF was within days of being destroyed when the German brass made a really stupid decision and began bombing London. The airfields had been bombed so much that if Hermann Goering had continued bombing the British airfields, the Battle of Britain may have gone very different. But the British could not make airplanes fast enough. They didn't have the capacity to do it. They came to their American allies. Understand that Theodore Roosevelt and Winston Churchill were distant cousins. This is what drove the Europe First philosophy during America's involvement in World War II. I have actually read a communique to General Marshall from Roosevelt saying, I understand the Japanese attacked us. I understand what you're saying. My philosophy is always going to be, we will beat the Germans in Europe first because the war was familial. Winston Churchill was part of Roosevelt's family, and Roosevelt was a distant cousin and family of Winston Churchill. And Churchill knew the Americans had the capacity, once it got going, to outproduce everybody, which we did. That's what got us out of the Depression, is World War II and everybody working, building material here at home or fighting the war. Because of this, the Royal Air Force and the British Purchasing Commission came to New York City and established an office there. They wanted more airplanes, particularly the P-40 Kitty Hawk, which they were already flying. And they talked to one particular airplane manufacturer called North American Aviation. Now, North American Aviation during this time period was making some fabulous airplanes. The B-25 Mitchell, which the British were also flying, and this P-40 Warhawk. But Dutch Killenberger said, hey, Brits, give us some time and let us design a better airplane using more modern processes than the P-40. The P-40 had an Allison engine, which a lot of American fighters were flying with at the time. A pretty good engine unless you went over 20,000 feet. And then its performance dropped off. Remember what I said, range, payload, endurance, and how important engines are to that. Dutch Killenberger and Edgar Smudge go to work on this new aircraft design. And in 102 days, come up with a new airframe and a new airplane. It is designated XP-73A. XP-73 Alpha. And it's got the same Allison engine in it. They try to figure out a name for it. And the first name for it given to it is A-36 Apache. And that sticks for a while. But as they begin to build more and more of these things, they begin to see this is really a unique design. And they redesignate it XP-51B. And they give it a name, Mustang. The original design of the P-51 is done in 102 days. From a white sheet of paper to the first airplane coming off the assembly line in 102 days. Now, we could never do that in this day and age. But back then, they could. And they did. And of course, the Mustang goes on to be this fabulous airplane. But it's got a problem, and it's its engine. The Allison engine was really good up to about 20,000 feet. The British take delivery of a bunch of them. The Americans are flying them too, but the performance just isn't there. They need to go higher because remember what I told you? Air combat, sea level to 30,000 feet, and sometimes even higher. The bombers are flying in the mid to low 20s. So if you can get up to 30,000 feet, you can really be someone in this airplane. In August of 1943, the 8th Air Force launches one of the largest air raids ever. And it's just called Mission Number 84. Mission Number 84 takes off with over 350 bomber airplanes. Spitfires and the Republic P-47 Thunderbolt with its big Curtiss Wright R-2800 radial engine escort the bomber force up to the French border, but cannot go any farther because they don't have the range. These bombers continue on to their targets in two German cities called Schweinfurt and Regensburg. They are intercepted by German aircraft 10 minutes after they go across the French border. German Luftwaffe airplanes are on them. Now, they're all in what they call battle boxes, okay? With a B-17 in each corner, and they have 10 different guns on the B-17. They're all firing these guns at these Luftwaffe airplanes. They have no fighter escort, and these lumbering bombers are these big, fat, fuel-laden targets going to these two cities. One that manufactures airplanes, the other ball bearings. By the time they drop their bombs, turn south and head toward the Alps, they've lost 60 airplanes out of 350 plus airplanes. There's 10 men in each B-17 bomber. 600 men are either killed, missing in action, or become POWs. And these bombers are literally falling all over France, Germany, because they're being shot down. The Luftwaffe actually has time to land, rearm, refuel, go back up after they've struck their targets and shoot more down. So they get tapped twice, 60 bombers. But there's nothing the American fighter force can do about it. The P-47 with its R-2800 radial engine and the amount of gas it carries, and because it's big, only gets less than 1.8 miles per gallon of gas, which is why it cannot go to any targets inside Germany. It doesn't have the range. 90 of the airplanes that make it back to their bases are so shot up that they're beyond repair. It's uneconomical to even repair them. 17th of August, 1943. The Germans have established air supremacy over their own homeland. A couple months later, October of 43, they do the exact same thing. 350 plus bombers take off out of England and head to the exact same targets, Schweinfurt and Regensburg, with the same results. 60 more airplanes shot down and 60 to 70 so shot up they'll never fly again. Lots of men killed in action, missing in action, and those missing in action, some of them become POWs and are now in Germany for the rest of the war. 26% of the bomber force in 2 missions are shot down over Germany because the American Air Force does not have an airplane, a fighter plane, with the range to go to Berlin and back. It's a real problem. And the Germans have established air supremacy over Germany with fighters and flak. In other words, anti-aircraft artillery, AAA. The bombers can't do it. They can't go there. We can't sustain those kinds of losses in a continuing air campaign over Germany. So what's the solution to this? About a year prior to these losses, a Rolls-Royce test pilot by the name of Ronnie Harker climbs in one of these A-36 Apaches and takes it up for a spin. Flies it to the max extent possible, does all kinds of things in it, comes down and lands. And he tells the Americans, nice airplane, terrible engine. The performance in this airplane is really good, 15 to 20,000 feet. Above that, you've got a real problem. But Rolls-Royce has the solution. And he tells them, you need to put Merlin engines in your Mustangs. He writes a report later on stating all of the performance limitations of the Allison engine versus all of the pros of the Mustang engine. And that report does make it back to the States, to North American Aviation, as a matter of fact, and they're reading through it. And they realize, you know what? You're probably right. We need to put a Merlin engine in this. The problem is that they run into is politics. Leadership in Britain goes, nope, we aren't going to do that. We aren't going to put our engines in American airplanes. First of all, we don't have the capacity to do it. We're already running engine manufacturing at 3 of our plants and a Ford plant in England, and we can't keep up. The assistant air attaché in the London embassy shows up to help save the day. His name is Tommy Hitchcock, and he's a polo player. Matter of fact, he's in the Polo Hall of Fame now. And he reads this report, and he's like going, we've got to do this. If we're going to be able to continue to fight over the German countryside, we've got to have an airplane that'll get there. But he goes back to Wright-Patterson Air Force Base in Washington, D.C., and they're all like going, no, that's a British engine. We're not going to do it. But Rolls-Royce comes over and finally gets the Secretary of State to look at this and the War Department to look at the reports and everything. And they go, okay, well, yeah, maybe let's do this. All right. But the first place they go, an avowed isolationist, he's saying, I'm only going to do things for the Americans. And that is Henry Ford. Now, think about this, folks. This is a $130 million contract in 1942, 1943. That's $2.2 to $2.4 billion in today's dollars. And Henry Ford says to him, okay, I'll make 6,000 to 9,000 of your engines, but I'm going to do it my way. And none of these can go to the British. And of course, the whole reason of doing this is because we need to help the British out. So he reneges on the deal and goes, nope, sorry, don't want to talk to you anymore, and sends him out of his office. So the American and British delegations sit down, look at each other and go, okay, well, where do we go from here? Where's the best place to get engines. That would be Detroit. So off they go to Detroit. When they get to Detroit, they say, who makes the best cars, the best workmanship, the best design, the best built? And of course, they're told, well, that's easy. That's like Rolls-Royce of America. That's Packard. This delegation goes to James and William Packard at their massive Packard Car Company plant in Detroit and give them a proposition. And they say, we need you to build these engines and mass produce these engines. We need them in Britain. You guys need them in your Mustangs. And they show them the report. In the report, the British had taken 5 of our P-51B models, named them Mustang X, and put Merlin engines in them. And their performance was phenomenal to 42,000 feet. The P-51 could fly at 440 miles an hour. But the best thing was a P-51 with a Merlin engine got 3.3 miles per gallon. The Mustang with a Merlin engine and its internal fuel load could get to Berlin and back. It had speed and range. So the Packard brothers go, okay, let's start doing this. And they run into a huge snag. The problem is the British design drawings are in metric. And the Americans, obviously, are in US standard. The other problem is the way their drawings are made. One is in first view, British are in third view. So it takes time to sit down and flesh this all out into new measurements. And that's one of the problems they have that kind of delays the Merlin engine. There's one more issue that they had to deal with, and that was tolerances. The tolerances of the parts. Because here again, there was 2 different philosophies. You have to understand when you have manufacturing tolerances that are so tight that you can mass produce the engines, but you have a company that's making the engines initially that do the parts so they aren't interchangeable. You can't mass produce them. Many of the Rolls-Royce workers were making the parts fit there on the assembly line, and you can't mass produce those. There's a key to understanding these manufacturing tolerances, or the lack thereof, and believe it or not, it was Ford, but it was Ford of Britain. The British Merlin engines were eventually built at 4 different factories. Rolls-Royce Derby, which is their main plant, plus 2 Rolls-Royce quote-unquote shadow factories at Crewe, which is currently the Bentley Works, and Glasgow, which is twice the size of Crewe, and it has its own foundry. But they are also making them at Ford in Manchester. The last factory began churning out engines in mid-1941, but not before Ford, like Packard, had to overcome a bunch of hurdles. Stanley Hooker's autobiography, Not Much of an Engineer, talks about how these things became a problem. Now, in his book, he talks mostly about the Rolls-Royce jet engines, but he was very instrumental in the Merlin development because he was the one who made the supercharger. He's the one that helped develop the supercharger that was in the engine. In the book, he says, in my enthusiasm, I considered that Rolls-Royce designs were the ne plus ultra until the Ford Motor Company in Britain was invited to manufacture the Merlin in the early days of the war. A number of Ford engineers arrived in Derby and spent some months examining and familiarizing themselves with the drawings and manufacturing methods. One day, their chief engineer appeared in Cyril Lovesley's office, which Stanley Hooker shared. I began talking with this particular engineer, and he said, you know, we can't make the Merlin to these drawings. Hooker replied loftily, I suppose that is because the drawing tolerances are too difficult for you, and you can't achieve the accuracy. The Ford engineer says, on the contrary, the tolerances are far too wide for us. We make motor car engines far more accurately than this. Every part on our engines has to be interchangeable with the same part of another engine, and hence all parts have to be made with the extreme accuracy far closer than you guys use. That's the only way we can achieve mass production. And there was the key. You couldn't mass produce the Rolls-Royce engines the way that they were being made. Now, the engine may have run better and smoother, the ones made by Rolls-Royce, but they had to be assembled and mass produced with much tighter tolerances. It says in his book, he says, Rolls-Royce was crafting Swiss watches. Ford was cranking out Timexes. And sometimes the occasion calls for a Timex. This was only sustainable because Rolls-Royce cars were fantastically expensive and it was produced in small quantities. To give you a perspective, the total Rolls-Royce automobile production between 1936 and 1939 was 6,244 automobiles. Packard sold 98,000 cars in 1940 alone because they could mass produce them. Because of these tolerances, they had to go back and look at all of the drawings so that all the parts were interchangeable, which they weren't with the Rolls-Royce engines. Now, once they started mass producing them, not a problem, because they'd worked all that out. But this was one of those other difficulties that they faced between the British Rolls-Royce engine and the mass-produced Packard engine that they had to overcome. And of course they did. The total number of Merlin engines produced was 168,068 of all variants, of which Packard had produced 55,523. One more thing that they had to deal with, the tolerances of the engines, because one was a Swiss watch, one was a Timex. When they finally do get some of the engines built, they put them in two Mustangs, and of course the Americans see the Mustang with the Merlin engine has phenomenal performance. 440 miles an hour, 42,000 feet, 3.3 miles per the gallon. And now they go, wait a minute, we can put external tanks on the airplane, 110-gallon tanks, and put an 85-gallon fuel tank behind the pilot, putting more fuel on the airplane, giving the P-51 a range of over 1,200 miles. Not only can it go from its bases in East Anglia to Britain, but it actually has some endurance time to find other targets of opportunity in Germany. Everybody sees the potential of mating the Merlin engine to the P-51s. Packard Motor Company walls off a whole area of its plant and begins building the Packard V1650 Merlin engine. Two-stage supercharger, new carburation system in it for the P-51s. And they can't come at a better time. This is in 42, and in 43, the Germans have air supremacy over their homeland. And this is about the time that 8th Air Force begins taking delivery of P-51s. Now, the old P-47 guys are going, nope, don't want it, nah, and they actually make fun of the Mustang. But they all become true believers later on. At the same time that it's being introduced, Jimmy Doolittle of the Tokyo Raiders fame shows up as the new 3-star general at 8th Air Force. The point-blank directive goes out in 1943, and it says, if we're to invade Europe, we have to destroy the Luftwaffe. And Jimmy Doolittle comes in, sees a sign above the entrance to his office that says, escort the bombers. And he immediately says, that's not our job. Our job is to go out and find the Luftwaffe and destroy them. Fighter command, go out, find the Luftwaffe and destroy them. And William Kempner, the fighter commander, goes, okay, boss. And they begin escorting the bombers. But because of the range of the P-51, they not only can escort the bombers, but can put P-51s out in front of them before the bombers even get to their targets, because now they've got range and speed and endurance, and they hunt the Luftwaffe down. 1,000 of their most experienced pilots are killed in the 1944 timeframe. Toward the end of the war, 8th Air Force is fighting literally kids. The P-51s are going all over Europe. But not only over Europe, in the Pacific, long-range Mustangs are taking off from Iwo Jima in the 44-45 timeframe and flying all the way to Tokyo, Japan, and doing the exact same thing, fighting the Japanese over their own homeland in these really long missions. Some of them 6 hours long. In Europe, 4.5 to 5. Now, in a propeller-driven airplane, that's a long time to be in the air. But all it took was an engine change in the P-51 to give it this outstanding performance and become the airplane that it is today. If you've been to an air show, the P-51 Mustang has a sound all its own. You can tell when a P-51's around because of the sound of this Merlin engine. Pushing this airframe 440 miles an hour. And oh, by the way, they figured out by putting the exhaust stacks pointing backwards, the exhaust gas coming out of the engine at 1,300 miles an hour gave the P-51s about 7 to 10 miles an hour more in airspeed. That was a new thing I learned researching this. There are 2 to 3 P-51s that you can buy in the ready-to-print area at wallpilot.com. In the late 1960s, the commercial and military world needed a new engine, and they needed it bad. The commercial world was already working with new engines on their commercial airplanes, and the company that created them was absolutely the beast, and that was Pratt & Whitney. But there was fuel efficiency problems and something new on the horizon, and that was noise reduction. Populations were moving in around the airports and were complaining about how noisy it was. Can we do something about the noise? But Pratt & Whitney had the cash cow, and that was the JT8D engine. It was the commercial version of the military TF-33, which was in the F-111s and the F-14s. It was a very reliable engine. Wasn't real fuel efficient, but it was a lot better than the J57 engines that had originally been put on the 707s, DC-8s, and other commercial airplanes. The KC-135 flew with J57s, the old water wagon engines, as we called them. We burned 13,000 pounds the first hour, 12,000 pounds the second hour, 11,000 pounds the third hour, 10,000 pounds the fourth hour, and around 8,500 after that. Very fuel inefficient engines. But the TF-33 was much more fuel efficient, but was still noisy. And the J-57s were incredibly noisy. I took off out of Riyadh, Saudi Arabia one night, and in the old A models, you would level off at 500 to 600 feet. In order to accelerate, I set off every car alarm in Riyadh, Saudi Arabia. We got a phone call when we landed back in England that all of the car alarms around the airbase we took off out of in Riyadh had gone off at 2 o'clock in the morning. So you can imagine there's a lot of unhappy people around the airports. The JT8Ds had pretty good thrust, but the best part about the JT8D engine was its great parts and services. You could fly into just about every airport around the world and get your JT8D engines serviced. And it was Pratt & Whitney's proverbial cash cow. They were raking in all kinds of money because in the commercial world, the JT8D was the engine to beat. And they enjoyed the top of the mountain spot. And all the commercial manufacturers were working on new planes. Airbus, Boeing, all working on brand new airplanes that needed higher thrust rated engines. At least what they call 10 tons or 20,000 pounds or more. And the JT8D didn't provide that. Everybody had to go looking. At that time, there was 4 engine builders. Pratt & Whitney was making military engines as well as commercial engines. And in the military world, their F-100 engine had been on F-15s and F-16s, but the government didn't like it. There was a lot of reliability issues, parts issues with the F-100 engine. The government had a kind of a sour taste in its mouth for Pratt & Whitney. GE, big military contracts. They had just won a big contract to engine the B-1 bomber with their new F-101 engine. But they were kind of a military focus. They weren't commercial focused. Snecma in France, they had been focusing on military engines. And then lastly, we've talked about Rolls-Royce. But Rolls-Royce was in a really critical time period because of the RB211 engine that they'd put on the Lockheed L1011 airliners. It was so cost overrun that Rolls-Royce was actually in receivership, bankruptcy. It kind of left them out in the weeds for any new projects. Snecma had a great charismatic leader by the name of René Ravaud. He meets Gerhard Neumann of GE at the 1971 Paris Air Show. Both of them at this same time period are thinking, you know, we need to look at making a 20,000 pound class engine. And they had been doing it privately amongst themselves. This relationship solidified beginning here at this air show. And René Ravaud starts looking for a partner. He'd already worked with Rolls-Royce, and that left a real sour taste in his mouth. And he knew Rolls-Royce couldn't do anything right now because of their financial situation. GE had the F-101 engine on the B-1, which was a great engine, but it's classified because it's on a Strategic Air Command bomber, the B-1. So there isn't anything they can really do about that. It's made with taxpayer money. The Americans don't want to send jobs overseas for making a new engine. There's all kinds of problems. A partnership with GE, Snecma and GE. President Jimmy Carter cancels the B-1. And now GE is kind of left after this big contract with basically nothing. The engine is being put in the fighters because there was this big competition for a fighter derivative engine, and the GE F-110 engine actually beats Pratt & Whitney out, and they go in F-14s and F-16s and give them more thrust, more reliability, all kinds of things. So it's really a good engine. But again, the core of this engine is still classified because it goes on military airplanes. The other thing that Snecma's got going for it is it's got money to build an engine. GE, not so much because of hurting from the B-1 being canceled. There's a great setup here for a partnership. Pratt & Whitney is out of the picture. They don't want to have competition against their JT8D. René Ravaud and Gerhard Neumann realize that Pratt & Whitney probably isn't going to want to do this. Why would they compete against their own cash cow? René Ravaud and Gerhard Neumann get their teams together and they say, look, you can make the fan section, we'll make the gas producing or the thrust producing section, and you can make the turbine section on the back of the engine, and we'll make this 20,000 pound class engine. The first CFM56 runs in 1974, and its performance is outstanding. It's really a good engine, and it's quiet. It's got 22,000 pounds of thrust, and it's very, very fuel efficient. Everything you want in an engine when you're looking at range, payload, and endurance. So now they've got this great engine, but they don't have any buyers. For almost 5 years, they don't have anybody that wants the engine because, again, Pratt & Whitney is the beast. And nobody wants this new, untried engine. Neumann goes after a State Department partnership approval, and it's disapproved by Henry Kissinger of all people. Henry Kissinger says, nope, this thing is classified, jobs overseas, our technology going overseas, we want to protect that. We're not going to do it. And it really makes the French mad, particularly after they've done all of this work with GE to make this incredible engine. The other thing they don't have, though, it's not tested. Newman and GE goes to Boeing and asks them, can you put these engines on your 707 test bed? And they go, sure. And they re-engine a 707, which is a KC-135 type of airframe with CFM56s. The performance of the engine is fantastic. They name the new airplane 707-700, and nobody wants it. And it gets canceled. And Boeing wasn't wholehearted into selling this thing anyway, because they've got their 757s and their 767s, brand new 2-engine airplanes that are coming out. So again, we've got the same problem. We have no customers for this incredible product. All of the performance shows that it's a great product, does everything it's designed to do, but nobody wants it. And in a meeting, Rene Ravaud says, if we don't get any customers for this thing in 2 weeks, we're going to shut down the program. And nobody wants that. Fortunately, the president of France, Georges Pompidou, wants this to go through. In a meeting in 1972 in Reykjavik, Iceland, with President Nixon, he brings up the CFM International Partnership. And they talk through it. You have these two great leaders discussing, how can we do this? Not how can we not do this, how can we get this done? And they come up with a pretty interesting solution. Because the engine is classified, GE and its craftsmen will build this classified gas core in the Evandale plant in Ohio and the Villaroche plant in France. But they'll do it in a special room where the French can't see it. And they make that restriction for 3 years. The next thing they do is they come up with a 50-50 profit sharing. No matter who sells the engine, the profits are split 50-50. Something that was unheard of during this time period. They still don't have any customers. And the French go, okay, tell you what, we've got 11 KC-135s. We'll re-engine our French Air Force KC-135s with CFM56 engines just to show everybody that they work. And they put these new engines on their KC-135s. And of course, the performance is just as expected. Fantastic. So now they go courting some of the commercial folks that are looking to re-engine their airplanes. They go to Delta, United, and Flying Tiger Cargo. All three of these companies fly the Douglas DC-8 stretched. Really long fuselage. But it's got old JT-8D engines on it. They kind of balk at it. They go, untested, we're not sure. And they're going, no, look, we got them on our KC-135s here in France. And so in this competition against Pratt & Whitney and their JT-8Ds with the new fan engine and all these different things that they've done to it, still doesn't satisfy the noise requirements, CFM International wins. And all the Delta, United, and Flying Tiger Cargo stretch DC-8s are re-engined with these CFM56s. And again, the performance is phenomenal. 40% increase in range on an airplane that's carrying over 150 passengers. So you're getting great revenue miles, but the big thing is you're saving gas, money on gas. And a bunch of other companies flying stretched 8s all fall in line and buy the engine. Now, the Air Force comes out with a request for proposals to re-engine the old J-57 KC-135s. And Pratt & Whitney is saying, oh, those guys, they don't build engines like we do. You know, the CFM guys, CFM just kind of goes, well, you know, we're getting some good mileage with these things. They're working pretty good. And there's 600 KC-135s in the Air Force's inventory. Guess who wins? CFM International and the CFM 56 engine. They start re-engineing all the KC-135s because they have all of this data showing it worked on these 707s, and the French Air Force KC-135s are doing real good with them. Let's put them on our airplanes. And they do. Now, I had the great honor of flying the old water wagon engines and the CFM 56 engines while I was stationed at Kadena. To give you an idea of how good this engine is, there was one particular mission we did with a Air Force spy plane, not the SR-71. With the old engines, it took 2 KC-135s to fly this mission and fill up this American spy plane. When we re-engined the KC-135s with the CFM-56, it only needed 1 tanker. We were saving a lot of money. We went from a 13,000-pound class engine to a 22,000-pound class engine. We could fly into 8,000-foot runways. We could take off with heavier fuel loads from shorter runways, like 8,000-foot runways. And it was quieter. But more importantly, the engines paid for themselves because of the gas savings. Over the period of a number of years, the Air Force saved so much money in gas because it went to these new engines that the program kind of paid for itself. The Boeing 737 jetliner was created as a small, short-range kind of puddle jumper airplane. It had really old engines. They were noisy. And the CEO of U.S. Air came to CFM International and said, we need to put these on the 737. And Boeing's like going, don't know about that. Because the 737's kind of squatty. It has really short landing gear. And the inlet of the CFM56 is very big. The CEO of Southwest also comes to Boeing and says, look, I need an airplane that's got greater range. And this engine is probably going to provide it to us. So what does Boeing do? All right, let's take a look at it. But they have to make some changes. Because the 737 is so squatty and Boeing wasn't about to change the main strut length at all because of the expense, they make the bottoms of the engine kind of flat. And they move this gearbox around to the side so that it won't get damaged. And they go and put CFM56 engines on the 737s. And the rest is history. There is no 737 that you don't fly on anywhere that doesn't have CFM56, even the later model engines that are producing, I think, 32,000 pounds of thrust. It was such a great engine for that little airplane. It could fly from coast to coast, and now they even fly from the West Coast to Hawaii. The CFM56 engine has now become the most mass-produced engine in the history of aviation. There are over 33,000 of these engines built and operating. I've only had to shut down CFM56 engines twice in my KC-135 R model career. Once was because we broke an oil seal and all of the oil in one of the engines went out and you had to shut the engine down. It windmilled for another hour until we could land at Misawa Air Base in northern Japan, and there was no damage, even with no oil in it. What happened in the second instance was we had what was called throttle bursting. The main engine controls computer card went bad, and the engine was going 96 to 58 to 87 to 62, and the nose was going everywhere, and we had to shut the engine down and bring it home. I had to dump 102,000 pounds of gas to get to our landing weight. It took us 20 minutes. But that's the only time I've ever had to shut these engines down. They're extremely reliable engines. And the best part is I was flying from Hawaii back to Okinawa, and we were burning 8,500 pounds an hour. Doubled the offload of the airplane. And that's exactly what the KC-135 needed. Remember, range, payload, endurance. This thing had a very bumpy beginning, but now has sold over 33,000 engines and is continuing to sell. And they're continuing to make better engines. There's now the Neo engine that's got a new fan in the front that's more efficient. The airplane burns less fuel, more thrust. There's all kinds of new engine technology coming out with the CFM56. And it's a fantastic marketing, and contemplating some of the lessons learned from this episode, I thought about one of Murphy's laws of combat. These are kind of the counterintuitive laws of combat. And one of those laws is, if it's stupid, but it works, it's not stupid. In each instance that I've talked about today, the Merlin engine and the CFM56, a lot of people thought, this is a crazy idea. I don't know if this is going to work. I don't know if this is the right thing. But there's a quote by Ayn Rand from The Fountainhead. And it says, every great new thought was opposed. Every great new invention was denounced. The first motor was considered foolish. The airplane was considered impossible. The power loom was considered vicious. Anesthesia was considered sinful. But the men of unborrowed vision went ahead. They fought, they suffered, and they paid. But they won. Think about all of the high-value business that these two engines created, even though people thought, this is not really a good idea. I don't know if we should do this. If you're in business and not willing to accept risk, then you shouldn't be in business. And both Rolls-Royce and Packard and GE and Snecma took a very high risk with an unproven engine in airplanes and won bigly. 55,000 engines, 33,000 engines. These are historic numbers. There's never been anything like this in aviation. The other thing I learned from this, and being in the business world, particularly the defense industry, is working with your international partners can sometimes be really interesting. There was a lot of times we couldn't find common ground. Or the processes were different. Or the way that they did their drawings were different, just like at Rolls-Royce. But these people had vision and they figured it out. And sometimes sitting down and nugging these things out, it's hard work and it's challenging. And sometimes the frustration level is really, really high. I went to a class by Dardis Communication on sales, and I learned something really, really important. And once we married all of this up, it was incredible what we could do. When we showed our customers this was the product for their solution. Here is the initial equipment buy. Here's the install cost. And more importantly, here's the price of services for the next 10, 15, 20 years. We were unbeatable. And that was because we had come to some common ground with this particular customer. And he had some pretty interesting restrictions too for a helicopter that they were buying and the manufacturer of that helicopter. But we were able to figure all of this out. And at the end of this meeting, this Air Commodore said, "Why wouldn't anybody come to you and buy this stuff? You've laid out 20 years of cost. I can see the risk in the paperwork here." And they went on to sign 5, 10, and 15-year contracts with us, worth several $million. As with any business opportunity, there's always going to be obstacles. Innovative solutions to complex issues is going to take time. I had a great Army general that taught me this very important kind of mental process. He called it the elements of the decision maker's dilemma. And those 4 elements are risk, time, quality of knowledge, and outcomes. When you're trying to create a new product for new solutions that are really out there and are really leading edge, you're going to go through risk, time, quality of knowledge, and outcomes. But if you have quality knowledge, you reduce risk, he said, because you act with more certainty with a reduction of second and third order effects. In every one of these situations, the Merlin engine they put in 5 Mustangs, found out great performance, all the way to 42,000 feet. But more importantly, it could go to Berlin. The Mustang could go to Berlin. Same thing with the CFM56. They put it on a 707 airframe, just like the KC-135, found out that, hey, the performance is great. We just doubled the offload capability of the KC-135 because they had the right information and it came in a timely manner for them to make good decisions. Rolls-Royce and Packard, Snecma and GE were able to put their engines in like airframes and test them. They had good quality information. Now, getting people to accept it is a completely different thing. And they had a big hill to climb in both cases. But they were able to do it because they had good quantitative data. When you can go up to your customer and say, I can double your range or your offload capability, you can now go into shorter runways and take off with larger fuel loads, with a more reliable engine that isn't going to break on you every 1,000 to 2,000 hours. And you have the service agreements to work on the engines, to replace the engines, replace all the parts. That's what every company's looking for. And look what happened in the case of CFM. They beat the beast. They beat them twice, both in the commercial world and the military world, because they had good information, they had good leadership, and they had a great sales team. You can find prints of P-51s for the walls of your home or office at wallpilot.com, our sponsor for this episode. On our next episode, I'm going to tell you about a time where I was in combat and it was pretty scary. Walking into the building, the planner that I had known for a while, D. Wright, looks down at my crew and says, "Are you coming in to fly?" "Yeah, we're coming in to fly." "Your mission's canceled. Go to mission planning and wait for me there." And what he had awaiting us was pretty shocking. It's also a great lesson in trust and relationships. On our next episode of Lessons from the Cockpit, please share this episode and all other episodes with your friends, and you can find them at my website, markhasera.com. I hope you've enjoyed this episode on engines, and we look forward to talking to you again next week.